Hello students, welcome to Edu-ca-te. Let us talk about the gradient of multivariable function. So you know that for any single variable function, for example, we are given here this parabola, we know that we can actually find the gradient or the rate of change of the function value with respect to x. Because this is actually a function of x, f of x is equals to x squared. This means that the y value or the function value depends on x. Hence, if we can try to find the first derivative, we are basically looking at the gradient or the rate of change of the function value with respect to x. So we know that for a curve like this one, the gradient is not consistent. The gradient differs with particular x values. So we can actually take the first derivative and we find that your gradient it is still expressed in terms of x. For example, using the power rule here, you can just say the derivative of x squared in terms of x, that's going to give you 2x. So here, this describes the gradient at a particular x value in this particular parabola. So in this case, we can try to put a tangent line at a particular x value. Let's just say, for example, the x value here is -1. So you can see that the tangent line is actually sloping downwards. So it means that is a negative gradient. So we can calculate the gradient simply by substituting the x value at which we are measuring the gradient, which is -1, and substituting it into this equation, you get that the gradient is -2, of course. And then you can also put another line here, this blue line. You can see that it is laying flat or it is horizontal. So this tells us the gradient is 0 at that point. You can just substitute the x value of 0 into the equation of the gradient, and you find that the gradient is 0 at that point. And then you can also do the same thing, put another tangent line at approximately, maybe let's just say the x value here is 3. Just for example, this is not drawn to scale, but basically here when the x value is 3, you just put 3 into the x and substitute 3 here where there is x in the gradient equation, which is the first derivative. You find out that the gradient at x is equals to 3, it is 6. So basically you can see that the gradient is not consistent within the function, it changes within the curve. So basically we can find the first derivative to be able to determine the gradient with respect to x, because we are sure that our function value changes when x changes. So for multivariable function now, we have got our function value depends on multiple variables. It can be 2 variables, or it can be 3, or it can be more than 3. So now in this case, this is an example of a multivariable function. You can see all of this shape, it is the multivariable function. This shows that this is the gradient of a function at a particular x or y or z value. This can be more variables more than these. So basically here, to find the gradient of a multivariable function, you have to first calculate the partial derivative of the function in terms of in terms of x first, and then you calculate the partial derivative in terms of y, then you calculate the partial derivative in terms of z. Then you add all these 3 partial derivatives. You just substitute here I. The I stands in for x-axis. Remember that the unit vector along the x-axis is known as vector I. And then the j stands for the y-axis, and the k stands for the z-axis. So basically you are trying to find out the rate of change or the first derivative of this multivariable function. Independently, you are trying to find the partial derivative, because remember that the first derivative tells you the gradient. So now, for example, we've got g at xy is equals to xy plus y times e to the power of x. So if they say find or determine the gradient of the function g, you would say that the gradient of the function g at xy at a particular x and y value, it is equals to the partial derivative of g in terms of x. And then now you're gonna put I there to say that you are on the x-axis, and then this is plus, you do the partial derivative of g, now you are doing it in terms of y, and then now you write j there, plus you do another partial derivative of the function value of g with respect to z. Now you are in the k direction. So now basically here, remember that when you're doing the partial derivative, you focus on that variable that you are deriving with respect to. In this case, you can see that you have got xy plus y e to the power of x. So if we find the partial derivative in terms of x, this thing contains x indeed. So if we differentiate this in terms of x, we remain with y plus, and if we differentiate this also in terms of x, this will be y times e to the power of x. So this is all the partial derivative in terms of x. And then you're going to write I to say that this is the partial derivative in terms of x. Plus, you do the partial derivative in terms of y. This function here is y. So if you do the partial derivative, you remain with x. You remain with x. And then plus e to the power of x. So this is the partial derivative with respect to y. So you're going to put a j next to it. Then this is plus. Now you're going to do the partial derivative in terms of z. But in this case, this is only given in terms of x and y. So we will not have a z partial derivative. So basically these are the partial derivatives. This is with respect to x, this with respect to y. So the sum of those two partial derivatives is known as the gradient of the function. Basically, you are finding the first derivative, but now you are doing it partially with respect to certain variables or certain x's. So basically, you are not allowed to add the values that are found here under I and the ones that are found under j. So this will be just your final answer as the gradient at g of x is to y. So this is generally the gradient at a particular x and at a particular y value. So if they can say maybe evaluate the gradient when at a point P given by x is 1, y is okay, let's just say x is 0 and y is 1. So now we have the equation of the gradient. Now you can say that the gradient is g. Now we are doing of when x is 1 and okay, when x is 0 and y is 1. So you're just going to substitute the values here. So when x is 0 and y is 1. So where there is y, you're going to put 1. Where there is x, you're going to put 0. So this is 1 times e to the power of 0. And then this is I plus, this is x. This will be 0 plus e to the power of 0. This is j. So in this case, the sum of 1 plus e to the power 0 will be just 1. So this will be 2, and there's an I. So this is 2i. And then this is plus 0 plus 1, that would be 1j. So this is your gradient of g at a point 0 is to 1. So to find the gradient, basically, you find the partial derivatives and you add them. You actually combine them or you actually separate them using a plus sign, but you do not really add them. In this case, you've got 2i plus j. Do not add 2 plus 1 and say that you have 3ij or something like that. No. Basically, when you are here, you are done. So this tells us a lot that the gradient of a multivariable function is actually a vector. So most of the times when we refer to it, we won't say the gradient. We'll say that this is known as a gradient vector. So it's a gradient vector given by these components. So it's a gradient vector given by the components 2i plus j. Okay, so basically here, that's how you find the gradient. You find the partial derivatives. Let us do an example. So given that f of xy is equals to x times y e to the power of negative x squared plus y squared, and now they say find the gradient of the function at point P given by x is 1 and y is negative 1. So now, first of all, remember to find this, you need to find the partial derivatives. So I'll just do this separately and say now the partial derivative of f in terms of x of this function will be given by, if we differentiate in terms of x here, you can see that there's x here, so and there's also x into the other part, and we can see that here these are separated by a multiplication sign, so we need to apply the product rule to solve it. So now do watch my video on partial derivatives if you are getting confused on how to do a partial derivative. So here basically you are going to find the derivative in terms of x of x. You're gonna find it of x, all right, and then Of course, this y, we can just treat it as a constant, or we can just say of xy, it's fine. You can just say this is of xy times, you will keep e to the power of negative x squared minus y squared. We just distribute the negative sign so that it becomes easier for us. Okay, and then this is plus the derivative in terms of x, because remember we're doing the partial derivative in terms of x, so we should do the first derivative in terms of x. So now we're going to differentiate e to the power of negative x squared minus y squared, and then now this is multiplied by xy without deriving it. Okay, so in this case, differentiating xy in terms of x will remain with y, and then this is e to the power of negative. You can just write it as x squared plus y squared. It's fine. There was no need for that distribution. So now this is plus. If we differentiate this, this is an exponential function, a natural exponential function. So we'll just rewrite e to the power of negative x squared minus y squared exactly as it is. Then you're going to multiply by the derivative of the exponent. In this case, the exponent is negative x squared minus y squared. And differentiating this in terms of x, you are going to get negative 2x. Y will just become a constant and we'll cancel it out. And then this is times x, y. So this is the partial derivative in terms of x. We're gonna get y e to the power of negative x squared plus y squared plus, here if you multiply the x values together, you get a x squared, and here this plus will just turn into a minus because here we've got a minus and a plus and you're multiplying them together. So now this is going to give us minus 2x squared y times e to the power of minus x squared plus y squared. So this is the partial derivative with respect to x. Okay, it was going to be a lot messy if I just mixed it all together. So this is the partial derivative of the function f with respect to x. So we can do the same thing and find the partial derivative of this function with respect to y. We want to see how does the function value change as the y value changes, basically. Here we were finding out how does the function value change as x changes. So now let us find the partial derivative now in terms of y. So the partial derivative of f in terms of y of xy will be given by, here you can see that we have got y in this first part, and then you also have got y in this exponential function. So you still need to apply the product rule, but now you are differentiating in terms of y. So this is the differentiating. We are differentiating in terms of y. We are going to differentiate the first part, which is xy. Then we're going to keep e to the power of negative x squared plus y squared. And then this is plus. Now we're going to differentiate e to the power of negative x squared minus y squared. I'll just be distributing and alternating this notation. You can see here. Then this is multiplied by xy without differentiating it. And differentiating xy in terms of y, you remain with x. Then this is times e to the power of negative x squared plus y squared. And then now if you differentiate this natural exponential function in terms of y, you just retain it exactly as it is, which is e to the power of negative x squared minus y squared, and then multiplied by the derivative of the exponent. The exponent is negative x squared, negative y squared. So here, differentiating in terms of y, you are going to get negative 2y. And then this is multiplied by xy. Remember that the derivative of y squared is just negative 2y. So now, to further expand here, we're going to get x e to the power of negative x squared plus y squared. And then this is going to be minus 2y squared x, and then you're going to have e to the power of negative x squared minus y squared. You can further factorize, or you can take out the e to the power of minus x squared and y squared. You can choose to do that. It's your own choice, but I'll just leave it like this. So now to find the gradient of the function, you're just going to add the partial derivatives. So this will be the gradient of this, the gradient of the function f of x, y. To find the gradient of the function f of xy, you're just going to take these and you add them. I've already written the formula before. So this is the partial derivative in terms of x. It is given by y e to the power of negative x squared plus y squared, and then this is minus 2x squared y e to the power of minus x squared plus y squared again, and then this is all the partial derivative of what? Of x. And remember that on the partial derivative of x, we're going to put a unit vector I. So next to the partial derivative, I'm going to write I here. Then this is plus. Because we are computing a gradient, we need to add the values. So we need to add the values because we are computing the gradient. Sikhona emnyango basically. Sikhona emnyango ndoda. Thatha ukhe ndoda uhlohle phakathi ndoda uvule. Oh. Okay. So basically here, you're going to add with the partial derivative of this function in terms of y. In terms of y, we found out that we get x, and then this is e to the power of negative x squared plus y squared, and then this is minus 2y squared x e to the power of a negative x squared minus y squared. And then now you found this, and then now you're gonna write j next to it. So the j symbolizes that this is actually a what? This is a partial derivative in terms of y. So you're just gonna multiply with the j next to it. And then now you want to evaluate the gradient of this function at the point p1 is to negative 1. So now we're just gonna say this is a point 1 is to negative 1, and then you wanna substitute. Where there is y, you're gonna put negative 1. Where there is x, you're gonna put positive 1. So this will be just y, which is negative 1 times e to the power of negative 1 squared plus negative 1 squared. So now you just do the substitution. You're substituting where there is x, you put 1. Where there is y, you put negative 1. So this is minus 2 times 1 squared times negative 1 times e to the power of negative 1 squared plus plus negative 1 squared, and then this is all under I. This is all under I. You're gonna put I next to it because there's the partial derivative in terms of I. And then you do the same thing. You substitute even the partial derivative in terms of y. But your final answer must be a gradient vector. It must be a vector. It must be in terms of I and j. It shows that it's a gradient. Thank you for watching, ladies and gentlemen. Don't forget to stay tuned to our next video.